The tech industry is shifting focus. We are moving from simply building models that generate text toward engineering intelligent agents that take autonomous action. The term agent gets thrown around a lot, but a standard large language model, or LLM, a system trained to predict the next word in a sequence, is not an agent by itself. An LLM operates at what we can call level 0. It acts as a powerful reasoning core, but it functions entirely in isolation. It has no external tools, no persistent memory, and cannot interact with its environment. Because of this isolation, a level 0 model cannot execute multi-step goals. If it encounters an unexpected obstacle or changing conditions, it cannot adapt its approach. It relies entirely on its pre-trained knowledge base. If you ask it for live data, like a stock price or the result of a recent election, it is completely blind. To achieve true agency, we cannot just scale the size of the model. We have to build a specific computational architecture around it. This diagram illustrates the Agentic AI problem-solving process. This 5-step loop transforms a static model into an active system. It moves sequentially, getting the mission, scanning the scene for context, thinking through a plan, taking external action, and finally, learning to improve future accuracy. Many early attempts at building agents tried to force this entire loop into a single massive instruction block, known as a monolithic prompt. Feeding a complex, multi-constraint task into a single prompt overloads the model's cognitive capacity. The model suffers from instruction neglect, where it ignores parts of the prompt. It experiences contextual drift, losing track of the initial goal, and early mistakes amplify through error propagation. Relying on a monolithic prompt to execute autonomous action is an architectural dead end. To guarantee reliability, developers use specific structural design patterns. This schematic outlines the prompt chaining pattern, a divide-and-conquer strategy. Look at the flow starting with prompt 1 and agent 1. The system performs a single operation. That output becomes the validated input for the next agent, creating a dependency chain returning a completed output. Consider processing a complex financial document. The first step uses one prompt to extract raw text. The second step normalizes that text into standard numbers. A third step routes those numbers to a calculator tool to perform arithmetic. This modularity lets the system interact with external databases or APIs at precise moments, without overwhelming the language model with too many instructions at once. To keep the chain from breaking down, developers force the model to pass data between these steps in strict, structured formats like JSON. JSON, or JavaScript Object Notation, is a standardized, machine-readable text format that prevents natural language ambiguity from crashing the sequence. Isolating reasoning steps into a strict sequence dramatically increases the system's accuracy and makes it possible for engineers to debug exactly where a failure occurred. Writing clever phrasing for a single prompt is no longer the primary driver of performance. The focus has shifted to context engineering. This diagram visualizes context engineering, the programmatic construction of a rich informational environment delivered to the AI. Notice the specific nodes feeding into the center. The system automatically injects historical state data, documents retrieved via RAG, retrieval augmented generation, and live data from tool outputs. Engineers use automated tuning systems to programmatically test and refine these contextual inputs across thousands of interactions, optimizing the environment at scale without manual rewriting. An agent's capability comes from the structural richness and precision of the data provided, rather than the linguistic cleverness of a single user query. While prompt chaining is highly reliable, linear sequences are rigid. If a user's intent is ambiguous or unexpected, a fixed pipeline will fail. This workflow illustrates the routing pattern. It introduces conditional logic, allowing the system to make dynamic decisions. The central router block evaluates the user's initial prompt and determines the exact sub-agent or tool required, as shown by the diverging arrows. For example, an incoming customer query hits the router. If it's a routine account question, the router directs it to a database retrieval tool. If the language indicates a complex dispute, it triggers an escalation protocol to a human operator. This decision-making logic can be powered by an LLM explicitly evaluating the text by measuring semantic similarity using vector embeddings or through hard-coded keyword rules. By analyzing input and conditionally directing the workflow, routing turns a rigid script into an adaptive, context-aware decision maker. We are now entering Level 3 complexity. Developers are abandoning the idea of building a single, all-knowing superagent to handle every request. Complex challenges require a division of labor. Systems are now structured like human organizations, deploying teams of specialized agents that work together to accomplish multifaceted objectives. This enables the parallelization pattern. Instead of waiting for one step to finish, independent subtasks are distributed and executed simultaneously. A central project manager agent can coordinate a product launch by simultaneously deploying a research agent to gather market data and a design agent to draft promotional concepts. Executing independent tasks concurrently reduces overall execution time and prevents cognitive bottlenecks at any single point in the architecture. This chart maps the trajectory of Agentic architecture. The topmost tier, Hypothesis 5, represents the emergence of the goal-driven, metamorphic multi-agent system. In this paradigm, the user no longer programs an explicit execution path or maps out a routing tree. The user simply declares the desired outcome, and the system figures out how to achieve it. The system continuously analyzes its own performance. When it encounters a bottleneck, it modifies its internal topology to overcome the obstacle. It can autonomously spawn new, specialized subagents, duplicate existing agents to run tasks in parallel, and remove redundant nodes to form the most efficient team. Operating at a higher level, the system automatically performs its own context engineering, refining the specific instructions and data it feeds to each internal node without any human intervention. The future of software engineering is no longer writing explicit code to execute specific tasks. It is engineering the environments where autonomous cognition can reliably self-organize.